Welcome to Team 506 Pandara's control word submission from Palmer University High School. Our video is split into 4 sections, including autonomous algorithms, teleop algorithms, auto demonstration, and teleop demonstration. You can easily skip to any section of our video by utilizing the chapters built into this YouTube video. Let's get into it. Our custom computer vision is facilitated by an open source library developed by Intel known as OpenCV. This library allows us to access complex algorithms that we can use to manipulate in order to give us certain information. We created a custom OpenCV model that can detect how many rings are in the starting stack during the initialization period of autonomous. To do this, we created a virtual box around the rings that extracts the RGB value. Utilizing the methods from the OpenCV library, we then convert that RGB value to YCRCB, and we extract the CB channel to our CB variable to compare how far away the RGB values of the pixels in the virtual box are from the color red. Finally, we take the average CB value and compare it to our experimentally derived threshold values for 4, 1, and 0 rings. The strafe direction algorithm allows the robot to strafe at any angle while continuously facing forward within the autonomous period. The method utilizes 2 derived trigonometric equations that relate the power of the front right and the back left wheels to the power of the front left and back right wheels based on the inputted variable theta. Imagine a unit circle being constructed around the robot from a top-down perspective so that the 90 degrees on the circle correlates with the front of the robot. The method parameter theta describes the angle of the direction the robot is traveling in relation with that unit circle. This equips us to do more complex movement within the autonomous period and makes our autonomous paths much more time efficient. Our rotate method is equipped with the modified form of a PID control to guarantee an exact rotation to a desired angle. Similar to a normal PID control, the method decreases or increases the power based on both the proportion between the current and desired angle and the derivative, that is the angular velocity. What makes our method different is that we only begin with accumulating our integral term once the robot has sensed that the motors have stalled, also known as when the angular velocity is 0. It then incrementally increases the motor power until we reach the desired angle. The method allows for a more dynamic response to a stalling motor since it continues to allow the robot to rotate at a minimum angular velocity when close to a desired angle, regardless of the external factors such as friction and battery voltage. In order to shoot rings in the most time-efficient manner during the driver-controlled period, we utilize one-button shooting. All 3 rings are automatically shot with a click of a button. We tune the shooter's PID so that the shooter motor would get to the targeted velocity as quickly as possible. Once the robot detects the shooter is running at the correct velocity, the Lexan ring blocker is moved up and the intake pushes the rings into the shooter. Our robot can automatically detect when a ring is intaked through the use of a color sensor. To do this, we extract the red value of the RGB detection method from the Rev color sensor class, as the ring's color is closest to red. We then correlate any change of more than 20 in the red RGB value with the new ring being intaked into a robot. With this algorithm, we were able to automatically rev up the shooter when there are 3 rings in the robot, allowing us to save a significant amount of time in the driver control period. We created an algorithm that can automatically detect when a ring is shot. To do this, we detect the spikes in the shooter motor's amperage and correlate each spike with a ring being shot. We detect these spikes by constantly drawing the amperage of the shooter motor, and if there is an anomalous value, the algorithm adds 1 to the counter variable. With this algorithm, we're able to shoot each ring at a different velocity and automatically turn the shooter off when all 3 rings have been shot. Using the strafe direction algorithm, the robot goes forward at a 30-degree angle, then goes right at a 90-degree angle, and shoots the rings into the high goal. Then it places the first wobble goal down, turns using the rotate method, and goes backwards. It then proceeds to pick up the second wobble goal, goes forward, turns around, and delivers the wobble goal while parking with the arm. With a click of a button at the end game period, we can shoot all 3 power shots using our rotate, strafe direction, and ring detection algorithms. For more details about some of these algorithms, please go to page 13 through 15 in our engineering portfolio. Thank you for watching our control word submission, and we look forward to seeing you at the judging interview.